Welcome to your first semester of Probability Theory and Statistics at Delhi University. Today, we are going to explore a fascinating and foundational topic, continuous random variables. We will learn how to mathematically model things that flow smoothly, like time, weight, and distance, rather than things we just count. Let us dive in and build our understanding from the ground up. To begin, imagine you are counting the number of students in a classroom. You can have exactly 20 or 21 students, but you can never have 20.5 students. This is what we call a discrete situation. But what if you are measuring the exact time it takes for a student to run a race? A highly precise stopwatch might read 12.3456 seconds. Time does not jump in whole numbers. It flows smoothly, without any gaps. A continuous random variable is a mathematical tool used to describe these measured outcomes rather than counted ones. Now that we understand what a continuous variable is, we face an interesting mathematical quirk. Because a continuous variable can take on infinitely many possible values between any 2 points, the probability of it landing on one specific, exact number is actually zero. Think about guessing someone's exact weight down to the millionth of a gram. It is practically impossible. Therefore, instead of asking for the probability of one exact value, we always ask for the probability that the variable falls within a certain range. This brings us to how we actually calculate these range probabilities. To find the probability of a continuous random variable falling in a range, we use a special curve called a probability density function, often written as f of x. This function describes the shape of the probabilities over the number line. But be careful here. The height of this curve at any given point does not give you the probability directly. Instead, the probability is represented by the physical area underneath the curve between two specific points. Let us visualize this concept. Here you see a smooth curve representing a probability density function, f of x. Notice the horizontal axis represents a continuous random variable, x. We have marked 2 points, A and B. The shaded blue region between A and B represents the total area under the curve in that specific window. This physical area is exactly equal to the probability that our random variable falls between the values A and B. Now that we have seen the visual representation, let us look at the mathematical formula that makes this possible. To find the exact area under a curve, we use an integral, which is a fundamental tool from calculus. The probability that our random variable big X is between lower limit a and upper limit b equals the integral from a to b of f of x dx. Here, f of x represents the height of the probability density curve, and dx represents an infinitely small slice of width along the horizontal axis. When you increase the gap between a and b, the area gets larger, meaning the probability increases. This formula we just saw leads us to a fundamental rule for all continuous random variables. If we integrate our probability density function from negative infinity to positive infinity, we are calculating the total area under the entire curve. This result must always equal exactly 1. In plain English, this means there is a 100% chance that the random variable will take on some value in its possible range. If the area is not exactly 1, the mathematical model is invalid. Before we move on to more abstract ideas, let us see this formula in action with a concrete example. Suppose we have a continuous random variable, big X, that represents the lifespan of a cheap battery in hours. The manufacturer claims the probability density function is f of x equals c times x for the range between 0 and 2 hours and 0 everywhere else. We need to find the value of the constant c that makes this a valid probability density function. To do this, we set up an integral of c times x from 0 to 2 and set it equal to exactly 1, because the total area must be 1. Continuing with our calculation, we must perform the integration step by step. The unknown constant c stays outside the integral. The integral of x with respect to x becomes x squared divided by 2. We must now evaluate this result from the lower limit of 0 to the upper limit of 2. We substitute the upper limit 2 into the expression and then subtract the expression with the lower limit 0 substituted in. This is the standard way to evaluate a definite integral. 2 squared is 4 and 0 squared is 0, which simplifies our expression nicely for the next step. Now we just finish the algebra to find our constant. Inside the parentheses, 4 divided by 2 is 2. So the constant c multiplied by 2 must equal 1. By dividing both sides of the equation by 2, we isolate c and find that it must be exactly 1/2 or 0.5 for the total area to be exactly 1. This gives us a final valid probability density function. F of x equals 0.5 times x. The mathematical model is now complete, verified, and ready to use for calculating specific probabilities. Now that we have our valid probability density function, let us calculate a specific probability. Using the battery lifespan model from the previous example, what is the probability that a randomly selected battery lasts between 1 and 2 hours? To find the probability that the variable falls within this specific range, we need to calculate the area under the curve just for that window. We set up our probability statement on the left side. On the right side, we write the integral of our function, 0.5x, from the starting time of 1 hour to the ending time of 2 hours. We integrate the function just like we did before. The constant 0.5 remains outside, and the integral of x becomes x squared divided by 2. We prepare to evaluate this expression from the lower limit of 1 to the upper limit of 2. We plug in the upper limit 2 and subtract the result of plugging in the lower limit 1. Squaring the numbers in the numerators gives us 4 over 2 minus 1 over 2 inside the parentheses. We are now very close to finding the exact area under the curve for this specific time window. Let us simplify the fractions to get our final answer. 4 halves is 2 and 1/2 is 0.5. Subtracting 0.5 from 2 inside the parentheses leaves 1.5. Finally, we multiply 0.5 by 1.5. The final result is 0.75. In plain English, this means there is a 75% chance that a randomly chosen battery will last between 1 and 2 hours. This makes sense because the function gets taller as time increases, meaning most of the probability is concentrated in the second half of the battery's lifespan. So we have successfully calculated probabilities using integrals. This brings us to why this matters in the real world. Continuous random variables are the absolute backbone of modern engineering, science, and finance. Whenever we measure something in the real world, like the exact temperature of a chemical reaction, the precise diameter of a manufactured pipe, or the exact time a stock price hits a certain level, we are dealing with continuous data. Without this mathematical framework, we could not calculate manufacturing tolerances or predict the failure rates of mechanical parts. It allows us to model the smooth, unbroken flow of reality. Let us summarize the key takeaways from what we have learned today. First, continuous random variables represent measured quantities that can take any value within an unbroken range. Second, because there are infinitely many possible exact values, the probability of landing on one single exact point is always 0. Third, we find probabilities for a specific window by calculating the area under the probability density function curve using integrals. And finally, the total area under any valid probability density curve must always equal exactly 1. Great job following along. You have now mastered the basics of continuous random variables.